now we move on to Unit 6, which is trees and their energy transactions. We are going to start to look at individual elements in the next couple chapters, like trees and water and such, because they are some of the most important elements that we have in our designs. So we really want to get to know them really, really intimately. And as far as this section goes, we really want to focus on the energy transactions of trees versus just individual types of trees themselves. We want to know how trees behave and interact with our systems. So all ecosystems on Earth major in woody elements, trees in the canopies and in the understories. So they capture the sun's energy and they are able to convert it in numerous ways. So now's a good time that if you need to review any of the previous sections to get a really good hold on them, it's a really good time to do that. We are now heading towards looking at these specific elements that will assist with energy capture. And so trees are the first of these that we're going to study. So this unit is actually, it's about the part that trees will play in our system as opposed to what types of trees you should use. So the interactions of trees, it's very complicated. Condensation is a largely overlooked contributing effect that people tend to ignore because it's very difficult to measure. It's not the same as just sticking a rain gauge out in your yard and then reading the measurement after a rain. The interaction with condensation is the pressure between the leaf surface area and water vapor. And in this situation, the surface area of leaves is actually much larger than we realize. So when we're looking at a leaf and we think of its surface area, all we really think about in our mind is what we can measure with a ruler. So we basically think of the surface area as approximately this distance times this distance with a little bit shaved off for the shape of the leaf. And that's all we really see when we think of surface area. But leaves are a lot more complex than that. And if we look really closely at a leaf under a microscope, we can see that the leaf has indentations in it. So each one of these veins, or it almost, even if you look at your skin, it's kind of the same as the leaf where there's little tiny indentations and undulations in the leaf surface. And each one of these little indentations also has indentations as well. So when we start to add up this surface area along with all of this surface area, we notice that a large tree can very often have a surface area of 40 acres that interact with water vapor. So that is definitely not insignificant. And this means that there is a lot of condensation or drip potential that can exist. And this is most noticeable if you live at the edge of a forest and you have a tin roof. And it will actually sound like it's raining all night long. It might actually seem like the forest itself is actually raining. That's where, we get the term rainforest from. It's not just the fact that it's raining, but because it just seems to constantly be coming out of the air at all points in time. So in the humid climates, there's obviously a huge major condensation effect that seems quite apparent. But where it's the most important to take note of this condensation and to use it to our advantage is actually in the dry lands. Because this condensation can be a major energy harvesting element. So trees have many other interactions that are not counted by most designers. So one of these is that a tree tends to act like a hydraulic pump. So if we look at a tree, obviously we've got a lot of stuff going on under the ground with the root systems. I shouldn't have made my tree quite so tall. I'm running out of space here. So we still need to have the canopy on this. So what happens is when the tree is intercepting the rain that's falling, the leaves actually start to stand up in order to help direct the water towards the veins, and then that directs it towards the twigs of the trees, which directs it towards the trunk of the tree, and then down to the roots. So the water that's on the trunk, by the time it comes off of the leaves and onto the twigs and onto the trunk, that water is really quite frothy. And that's because it's carrying quite a bit of nutrient from all of these other surfaces that it had to pass down. The water then goes on down to feed the tap root ladder. So there's typically kind of one more major root that's going to kind of come down with some other roots coming off of it. And that's what gets fed by the water that hits the leaves typically. And once this is saturated enough to get a full hydraulic charge in the tree, then you start to get a throughfall of rain. So you can shelter under a tree for a certain amount of time, but once that tree is completely hydraulically charged and it's completely saturated, then that water will start coming through the canopy of the tree. So if you capture this water that's coming through the tree and off of the tree, it can actually be 50 times more nutrient dense than the rain before it hits the tree. So this is kind of a major point because it captures all of the dust and particles that were on the leaves. And this tends to feed the hairnet roots that are going to be more towards the surface of the ground. And that's why it's usually best to mulch in a ring out from the tree, because we want to collect all of that water that's going to feed the tree at a distance that is where those hairnet roots actually are, where the canopy kind of overhangs, instead of right up against the trunk. Because the right up against the trunk will automatically get watered just from these leaves standing up and redirecting the water. And then all of the throughfall and all that really nutrient-rich material will kind of collect more at the canopy edge here where it's dripping off. And that's where we really want to store that nutrient to be able to feed the tree better. So if we look at a little bit of facts about a typical tree, it doesn't really matter what type of tree we're looking at. Most of the biomass now we're talking about large trees here, like big canopy trees. So most of the biomass is actually in the top 2 meters of the tree. So if we look at a tree, there's going to be tons and tons and tons of foliage and branches and everything in the top 2 meters. And 15% of the biomass is in the top, 15% of the biomass and 90% of the water that's held in the soil is actually only in the first 2 feet of soil. So really there's not a ton of biomass there, only 15% of the tree, but 96% of the water is held there, which is pretty key. So because this tree is holding such an incredible amount of water in the soil, if we had kind of a large region of forest and we had a pond at the bottom that was collecting a bunch of water, and we've got a dam wall here so that things won't come so that the water doesn't run downhill, but there's a little bit of an overflow possible. And if we have a whole bunch of trees here, and suddenly we cut all of those trees down, what's going to happen is that 96% of that water that was held in place by each tree is suddenly going to get released down the hillside, and it's going to overflow this pond, and it's going to flood regions downhill very, very quickly. So this will happen even if it hasn't rained. So if these trees existed and it didn't rain, but we cut all of them down, suddenly this pond would overflow very quickly because all that water would suddenly be released. It wouldn't be held in the soil anymore. And when it rains the next time, then that water will just run too quickly down the hill because this is no longer a sponge-like area. And that water is going to run downhill way too quickly, and this is going to overflow and flood and cause erosion every single time after that point because that sponge is now gone. And we've turned this area, just by removing those trees, we've turned this whole area into a drought and flood kind of regime. So it'll go from being extremely dry to flooding, or extremely dry to flooding over and over again. If these trees were still there, then this would all come down the hill very, very gently, and the overflow would be extremely gentle if you had a heavy rain, and you would have a more maintained, steady flow of water throughout the terrain, and you would have minimal erosion in that situation.